Hello and welcome to our next lecture. This is the first lecture in our series of lectures about partial differential equations. And I want to begin with first talking about what a partial differential equation is. In your multivariable class, you have seen some functions that may depend on several variables. And when you start writing equations with functions that depend on several variables, then your equations may start having partial derivatives involved. Unsurprisingly, differential equations that are formulated in terms of partial derivatives are called partial differential equations. There are many different types of partial differential equations, and we're only going to scratch the surface. We're talking about linear differential equations with constant coefficients up to second order. So if we have a quantity that depends on two variables, say x and t, then we may have a differential equation that looks something like that. We have a partial derivative in terms of x twice. We may have some mixed derivatives. We may have derivative in terms of time. We may have single derivatives involved. Naturally, we may have a function itself in non-differentiated form involved. And there could be a right-hand side that depends on x and t only, where the left-hand side depends on x and t and the function u. The subscripts underneath the function indicate the derivatives taken. So for example, t means take two derivatives of u with respect to t. And we're talking about partial derivatives here. We're only going to talk about equations where a, b, c, and d, and e and f are constants. They do not depend on x, t, or u. And if g of t is 0, we call the equation homogeneous. Otherwise, if g of t is non-zero, we call the equation non-homogeneous. In the theory of partially different equations, the equations can be subdivided into three distinct groups. Each group is named after a physical process that it models, but also the solution techniques and the solutions themselves have completely different properties for these types of equations. The heat equation is the one that we're going to study first. It's the one that involves on the first derivative in terms of time and two spatial derivatives. There could be constant involved. And this is if you only have two dimensions. When you have only the time variable and the x as a space variable, there could be multidimensional equations of the same type. But the heat equation in several dimensions is still going to have one time derivative and second derivatives in terms of spatial variables. This type of equation is called parabolic because it seems like you have only one time derivative in terms of t and twice the derivative in terms of x. So if you start taking Laplace transform, then you have a t multiple on one side and x squared multiple on the other side. The second type of equation that we're going to consider is the wave equation that models oscillating physical phenomena. For example, oscillations of a string or oscillations in air pressure when sound travels through the air. These equations have both the time derivative and the spatial derivative of second order. There could be again a constant, and the multidimensional counterpart looks like this. These type of equations are called hyperbolic because, again, you can think about taking two derivatives in terms of time and two derivatives in terms of x, like multiplying by t squared, multiplying by x squared, and then t squared equals kx squared is the equation of a hyperbola. And the last type of equation is what we call Laplace equation, which doesn't have any time derivatives, only has the spatial derivatives, and only talks about either 2 or 3-dimensional phenomena. So you either have something like a uxx plus uyy equals 0, or uxx plus uyy uzz equals 0. Interesting to note that the Laplace equation is linked to the heat equation. So what if you have a stable state when no heat flows in and out of the system? Then the temperature, which is modeled by the function u, is going to stay constant in every position. And that means that the time derivative of the temperature is going to be 0. And if you make the time derivative 0 here on the left-hand side, then what you're left with is the Laplace equation. The summation of second derivatives of the function in terms of spatial variables is called the Laplace operator, and sometimes written as either nabla squared u, which is the gradient sort of taken twice, or gradient in dot product with itself of u, or a gradient of u, or sometimes just marked as delta u equals 0. This is just a notation there to shorten the expressions that you're writing. Instead of writing 3 terms, you can just write 1, and everybody knows what you mean by it. So let's talk about the heat equation and how we can derive it. We're going to look at the actual physical process of a heat transfer through a thin rod. So we're going to assume that we are having a thin rod of constant cross-section. We're going to assume that there is no heat transfer into the air, so it's completely insulated from the temperature on the sides of the rod, but may not be insulated at the ends. We're going to make several assumptions. First of which is that the rod is uniform. Meaning that it has the same cross-sectional area and same material all the way throughout with the same thermal properties. That means that the temperature that depends only on the position x of the cross-sectional slice and the time t, meaning that throughout the cross-section the temperature stays uniform. We're going to assume there is no heat loss through the surface of the rod, but maybe only the heat transfer through the ends. There are also several physical characteristics of the material that we need to take into account. One of which is the density, the specific heat, which is the amount of energy needed to raise a kilogram of material for 1 degree up. And we also make use of the constant K, which is the heat conductivity. Which is a constant that says how fast heat travels through the material. In order to derive the equation, we need to consider a small portion of this rod. say there's a tiny interval from A to B, and look at the happenings inside the rod only on that tiny interval. So if we're only looking at the tiny part of the rod, then we can see that the temperature can go only up or down for this thin portion of the rod if there is some heat pumped through the ends of this little section. Because there is no heat in exchange through the lateral surface, the heat can only come in from the left or from the right. From the physical principles, we can say that the heat energy accumulated in this thin portion of the rod is going to be a total integral of the temperature multiplied by the specific heat, by the density, by the cross-sectional area, and integrate with respect to x. And by the principles of conservation of energy, the rate of change of the thermal energy is the rate at which the energy flows into this little portion or section of the rod minus the rate at which the heat leaves that portion. So the rate of change of the quantity Q is the rate at which heat flows into the section minus rate at which leaves that little section. The rate of change of Q is definitely the time derivative of Q. However, we also need to quantify the heat flow in or out. So we're going to define a heat flux be the function that measures the flow of heat energy per unit cross-sectional area per unit time at a location x and the time t flowing in the positive x direction. So if the heat flux is positive, that means that heat flows from left to right. If the heat flux is negative, that means that the heat flows from right to left. Naturally, we would assume that the heat flux is only possible from the hot parts to the cold parts. When the heat flux is negative, that means that the heat flows from right to left. That means that the temperature on the right is larger than the temperature on the left, and the temperature gradient is actually positive. Having this observation, we can assume that heat flux is proportional to the derivative of u with respect to x. We saw that if the temperature gradient is positive, that means that the temperature increases as we go from left to right. Probably would mean that the temperature flows in the opposite direction. And that's why we have a minus sign in front of the K constant. So, taking apart the principle of conservation of energy, we can say that the rate of change of Q is a derivative of Q with respect to time, which means that I have to take the derivative of the integral from a to b of u of x t times density times the cross-sectional area times the specific heat dx. The time derivative can migrate inside the integral, and I would make the integral to go from a to b. But now the function u depends on two variables, and therefore the time derivative becomes a partial derivative. The rate of heat inflow and the rate of heat outflow really depends on what's going on at each end of my little section of my rod. So I'm going to break it apart into a rate of heat flow at the end x equals a, which is going to be the cross-sectional area times the heat flux at a and time t. So this is going to be minus k times a times du dx at x equals a. So if the heat flux is positive, meaning the heat flows from left to right, I will have heat entering my little section that I'm considering. On the other end, I get that the heat flow will be negative, the heat flux. This time it's multiplied by -1, because if the heat flux is positive, it would mean that the heat flows from left to right, meaning it would leave the rod at that rate. So it's going to be positive k times a times du dx at x equals b. So the total heat flow through the section is going to be the summation of those quantities When we talk about fundamental theorem of calculus, we often denote this operation as a function computed from a to b. And if I want to express it as an integral, it seems like du dx is the antiderivative of du dx twice. So it's going to be the integral from a to b of k times a times second derivative of u with respect to x twice integrated with respect to dx. And since the rate of change of q has to be directly equal to the rate of heat flow in and out of my little section, I can conclude that the integral from a to b of the partial derivative of u with respect to time times rho times a times c dx should be the same as the integral from a to b, k a times a second derivative of u with respect to x integrated with respect to x. Since a and b are arbitrary, it means that we're taking integral over all possible subintervals from a to b. And if these two functions inside integrals are different, even at some location, then we should be able to find the intervals a to b where those integrals would be completely different. But what the equation says that no matter what a to b you choose, this integral is always going to end up the same, and therefore you're integrating same functions. And therefore, du dt times rho a c should be the same as k times a times the second derivative of u with respect to x. Simplifying this, we arrive to the fact that the time derivative of u should be the same as k over rho c times u x x, where sometimes k over rho c is exchanged with a single constant, kappa. Where kappa is a Greek letter akin to the letter K. With this single constant, the equation looks a lot cleaner. And that's the equation that we're going to mostly consider. We can interpret this equation as this. So suppose I have, at some point of time, I have u given to us as a function of x. If this function is concave down, that means that the temperature right here is higher than the temperatures around it, and we would expect the temperatures to go down. Therefore, the rate of change of this temperature with respect to time, if we let the time progress forward, is going to be negative. We would expect the temperature to go down. On the opposite side, if we have a temperature profile given like that, then the temperature at this point will be expected to go up because everything around it is hotter than it is. So it seems like that the rate of change of the temperature depends on the curvature of the temperature profile in terms of x. And that makes complete sense, because that's what we would expect from the physical standpoint. Once we derive the equation, we need to look at a few typical problems that people consider when solving heat flow problems. One of those problems is a thin rod is being clamped at both ends, and at those ends the temperature is kept constant. The equation is always going to be the same. It's going to be the time derivative equals kappa times uxx. But there are several conditions added. If you remember in differential equations class, you have initial conditions. For the partial derivatives, you would not only have initial conditions, but you also need to have boundary conditions. So if the rod has a finite length, means that x belongs to an interval from 0 to some L, and t belongs to the interval from 0 to infinity. Which means that we're going to have boundary conditions meaning that we need to know what the function u is at every time at the 0 end, and what the function is at every time at the end x equals L. And with the 0 temperature ends, the temperature is set to be 0. Since this equation involves the time derivative, we also need to provide the initial condition for what happens at time equals 0. And that's usually given as some function of x. Intuitively we would understand that if we keep the temperature at both ends to be 0, then at some point the thin rod through the heat conduction is going to lose all of its heat and then have a 0 temperature all the way through that. But what is interesting is how this heat is going to be conducted to different parts of this rod. Another possible situation is where the rod is completely insulated from the environment. So not only it's insulated at the lateral surface of it, it's also insulated at both ends. But that would mean that there is 0 heat flux going through both ends, and as we know, the heat flux is described by the partial derivative in terms of x, and therefore we're going to have the partial derivative in terms of x to be 0. Equation again stays the same. It's ut equals kappa times uxx. Boundary conditions are going to be different. Now u of 0, t can be anything, but its partial derivative in terms of x has to be 0, meaning there is no heat exchange at the end x equals 0. And just as before, the heat profile at t equals 0 can be anything. And we're going to see that the first type of a problem leads to the sine series expansion of the function f of x, and the second problem with the insulated ends will lead to the cosine series expansion of the function f of x. There are also two other types. Of equations. When we have mixed boundary conditions, say we have an equation ut equals kappa times uxx, but the boundary at one end stays with a constant temperature, but at the other end it's insulated. Or we may have an insulation and a zero temperature at other ends. We may have u of 0t zeroed out as partial derivative, and then u of lt being kept 0. There are also things that we're going to consider is non-zero boundary conditions. So for all of those problems, what we're trying to find is a function u that is going to describe the temperature of a thin rod at every given moment of time. We have this thin rod, and we're going to look at its time progression and initially we may have some temperature distribution. So we may have zero temperature at both at one end or another end, or we might have zero flux at one end or another end. But what's going to happen is we're going to look at what happens with the function as the time progresses. So we're looking at the snapshots of this function for different times t. So it's going to be the function of two variables, and it's going to create a surface, but we must understand that the surface is like a movie where we're looking at a function of a single variable x for different times t, and we're going to observe its evolution through different times. In the next lecture, we're actually going to solve the first and second problem. We'll save the problem 3 and problem 4 to later times. And we're going to solve with the method that's called separation of variables. This is slightly different from the separable equations that you considered in your differential equations class, but the name of the technique speaks for itself. We're going to try to separate the variables to two different sides of the equation. And we're going to see that doing so will lead naturally to series expansion of the solutions. So the solutions that we're going to get are actually going to be expressed as infinite series. And unless the function f is very simple, most of the time these series are going to be infinite, so there will be no way to express the solution as a finite sum of certain functions. Okay, that's enough for today. Thank you for listening, and I'll see you in our next video.